Hi students, good afternoon. Mr. Myers here to go over gram-to-gram stoichiometry. It's an abbreviated lecture tutorial from class today. What I want to bring to your attention first is the stoichiometry roadmap that we've been referencing in class so far. The lighting is kind of terrible on here. There we go. So what we have here is side A. And what we've been able to accomplish so far calculation-wise is going from grams of one substance directly to moles of that substance using molar mass from the periodic table as our conversion factor. We've also been able to go from moles to particles using Avogadro's number, or moles to liters using molar volume, 22.4 liters for every 1 mole of substance. And we've been going back and forth through there, 1-step, 2-step, etc. And then recently we said, well, what if I have moles of one substance in a balanced equation, and I want to find moles of a different substance in that equation? And the way we go about it is this mole ratio or coefficient ratio, which helps to bridge the gap between side A and side B. Now, A and B can be any of the reagents used in a chemical equation. They could both be reactants, both be products, reactant and product, vice versa. The idea is that using a balanced chemical equation, we can go from moles of one substance to moles of a different one where we utilize those coefficients. Today, the goal is to demonstrate how we might go from grams of one substance to grams of another. We see from the roadmap that we can't go directly from grams to grams in one step, but rather by following the course from grams to moles, moles to moles, and then moles to grams. That marker's not very good, but I think you get the idea. So we're going grams to moles, moles to moles, moles to grams. Put another way, I'll write it out, where if we have A going to B, where A is our starting point and B is our end point, we can refer back to the roadmap later, but we have our start and our end. So we would have grams of A, and we would convert this to moles of A, then moles of B, and then grams of B. So looking at the map here, grams of A, moles of A, moles of B, grams of B. So we're just writing it out in a linear fashion. Going further, we know that we can find moles of A by utilizing the molar mass of A, which comes from the periodic table. We can change to moles of B by using the mole ratio or coefficient ratio. And then we can go to grams of B from moles of B using the molar mass of B. Okay, so this would be our thought process, and this is going to play out in the calculation that we're about to see as an example. Now, I do want to make a note with our mole ratio here that in our calculations, when we're doing molar mass, it's always X number of grams for every 1 mole of that substance. So when we're doing our setup, we should always be using 1 with the mole in those scenarios. However, the mole ratio utilizes the coefficients from a balanced chemical equation, so you may have a number other than 1 for moles. So just to be aware of that. So the best way to go about this and explain the setup is to dive into a problem. So in problem 1, how many grams of chlorine can be liberated or freed up or produced from the decomposition or breaking down of 64.0 grams of gold 3 chloride by this reaction? The equation is provided and it is balanced. As we've set up in class, we identify our start point and our end point, right? It's as if we're entering GPS coordinates and we're saying, hey, this is our starting location, this is the end result where we want to go, and then we can look at the roadmap to decide what's the best route, how are we going to get there. So the start point here is 64 grams of gold 3 chloride, and the end point is grams of chlorine. All right, so to get started at our start point here, we're going to do a T-chart. And we start out with what we're given, 64 grams AuCl3. Okay, and we know from what we saw before, right here, that we're going to go from grams of A to moles of A. So back to the calculation, we should see moles of AuCl3 and grams of AuCl3. Molar mass is always a certain number of grams for every 1 mole. I'm going to fill the grams in later. And then we have moles of AuCl3 on top currently. As we convert to our next unit, the new unit goes on top, and the one we're getting rid of goes on the bottom. Notice grams of AuCl3 cancel, and then moles of AuCl3 cancel. So far we're at moles of Cl2. Last but not least, we want to go to grams of Cl2 for every 1 mole of Cl2. Moles of Cl2 cancel, and we're left with grams. So what we've achieved here very quickly is the unit conversion setup going from grams of gold 3 chloride to grams of chlorine gas. Then we have to go back and fill in the corresponding information that's missing. So take a moment and work on calculating those values out. Here we have gold 3 chloride, 196.97, plus 3 chlorines, each at 35.45, gets us 303.32. For our mole ratio, according to the balanced equation, there are 3 moles of chlorine for every 2 moles of gold 3 chloride. And then our molar mass of gold 3 chloride is 70.9. Now just to reiterate, this is our endpoint. Here we used molar mass to figure out that step. Here we used a mole ratio. And then at the end, we used a molar mass as well. So to determine our answer, we're going to do the product of the top divided by the product of the bottom. And as we put this in the calculator, we have 64.0 times 1 times 3 times 70.9 divided by, and this is where we want to be careful. If I just do 303.32 times 2, the calculator reads it in a linear fashion and does order of operations. It divides it by 303.32 and then takes that result and multiplies it by 2. This is incorrect. So make sure that your denominator is in parentheses. And I did not use parentheses. There we go. Enter. The result that we get is 22.4 and some change. If we record with significant figures, we want to record 22.4 grams Cl2. And that is our final answer for this problem. If you'd like, you can find the product at the top, write it out, and then the product at the bottom, write it out and do the final division. That's fine. Just be sure that you are writing out the full intermediate calculator answers so we can round for significant figures at the end. All right, and we got one more quick problem here, hopefully quick. Calculate the mass of Agcl, silver chloride. So mass, this is our end, what we're solving for. That can be prepared from 200 grams of aluminum chloride and sufficient silver nitrate. The sufficient just tells us that there's enough of that material around. It's an excess, there's no number, so it doesn't affect our calculation or thought process now. So the start is 200 grams of aluminum chloride, and we want to find the grams of silver chloride. Our equation is balanced, so let's begin. We start with what we know. 200 grams of aluminum chloride. We can go from grams of aluminum chloride to moles of aluminum chloride. For every 1 mole of aluminum chloride, there is a certain number of grams of that substance, and the grams will cancel. Then we can say, we can go mole ratio, coefficient ratio, and change to moles of the new substance, Agcl, and moles of aluminum chloride go on bottom because we want to be able to cancel those units out. And then last but not least, we know in one step from our roadmap, we can go from moles to grams. In fact, that is our endpoint that we're trying to achieve. And for every 1 mole of silver chloride, there are a certain number of grams that we'll put in, and moles of silver chloride end up being canceled, leaving us with the correct unit being converted to. So to do the calculation, before we can get there, we need to know the missing information. Aluminum chloride, aluminum is 26.98, and we have 3 chlorines for a mass of 133.33 grams for every 1 mole. Next, we have our coefficient ratio. According to the balanced equation, there are 3 moles of silver chloride for every 1 mole of aluminum chloride. And last but not least, we have the molar mass for silver chloride, 107.87 plus 35.45, 143.32. And when we do the calculation, 200 times 1 times 3 times 143.32 divided by the mass on the bottom, 644.956 and change. We have 3 significant figures given in the problem from the 200 point. So we record 645 grams of silver chloride. That's it.